Hello everybody. I welcome you all to NCAS Geology class. Today I'll discuss on the topic that is hydrothermal process. What is hydrothermal process and how it is related to formation of ore deposits, that I will discuss. So let us start. Magmatic masses towards the last part of the magmatic cooling and crystallization produce a residual liquid or residual fluid that is rich in metals, non-metals and volatiles. This fluid is generally called as hydrothermal fluid, whose temperature ranges are between 50 degrees centigrade to 550 degrees centigrade. So, the magma after cooling and consolidation produces a fluid at this temperature range 50 to 550 centigrade, and in this temperature range the residual fluid that is derived from magma is found to be rich with metals, non-metals and volatiles, and this fluid is described as hydrothermal fluid. And this fluid gives rise to different types of economic mineral deposits, and the main processes which are involved in this process of hydrothermal deposit are the cavity fillings and replacements. So let us discuss how it gives rise to economic mineral deposits. This hydrothermal fluid is found to contain in solution the metals such as iron, gold, copper, lead, zinc, tin, mercury and volatiles such as water vapor, carbon dioxide, chlorine, bromine, fluorine, sulfur. So these are the elements which are found to be present in the hydrothermal fluid. Besides these magmatic derivatives of hydrothermal fluid, there are other sources of hydrothermal solution such as the sea water or meteoric water, which gets mixed with the intruding magma and produces hydrothermal fluid. Similarly, through metamorphism, which by dehydration reaction yields hydrothermal fluid. So these solutions give rise to mostly epigenetic mineral deposits. We are having two types of mineral deposits, one is syngenetic, other is epigenetic. Syngenetic mineral deposits are found to develop along with the formation of the rock that contains the deposit. But in case of epigenetic mineral deposits, the rock types have been formed earlier, and the rock types present openings. In these openings, the hydrothermal fluid gives rise to economic mineral deposits. So, the mineral deposits are later to the formation of the host rock, and here they are called as epigenetic mineral deposits. So, hydrothermal fluid mostly gives rise to epigenetic mineral deposits. And the deposits include silicates such as quartz, calcite, fluorite, tourmaline, epidote, chlorite, calcite, amethyst, topaz and barite. So these are some of the silicates which are found to be produced by the hydrothermal fluid. Besides these, the metallic components which get concentrated from hydrothermal fluid are pyrite, chalcopyrite, sphalerite, galena, bornite, tetrahydrite, energite. These are mostly the sulfides. And the conditions which are necessary for development of hydrothermal fluid, or the conditions which are necessary for formation of hydrothermal deposits are the following. There must be the availability of enough metal content in the hydrothermal fluid or in hydrothermal solution. These solutions should be capable of dissolving and transporting metals in solution. There must be availability of openings in the country rock where the hydrothermal fluid can pass, can react to the country rock, and can give rise to economic mineral deposit under suitable conditions of cooling, consolidation, and reaction. Most of the host rocks, if are found to be reactive to the fluid, in that case the deposit can be possible. But when the reaction is not possible, in that case the possibility of getting deposit is not high, because the hydrothermal fluid gives rise to cavity filling deposits or replacement deposits. In case of cavity filling, the cavities present in the contracts are found to be filled up from the hydrothermal fluid through crystallization of the metals present in the hydrothermal fluid. But in case of replacement, the contract must have to be of suitable composition so that the reaction between the hydrothermal fluid and that of the contract will take place, and under that condition, if the contract is highly favorable to react, in that case deposits may be possible. So the conditions that are necessary for the hydrothermal deposit are that the hydrothermal fluid should be rich with the metals, the openings must be there in the country rock in sufficient quantity, and the contract should be of suitable composition to provide reaction with the hydrothermal fluid. Now let us see the causes that promote the mineral deposition. The causes are the change in temperature, change in pressure, exchange reaction between the substances in solution, that is mixing of magmatic and meteoric water, the exchange reaction between the solution and the wall rock, change in pH and EH of the medium, coagulation of the colloids brought about by exchange reaction, that is by breaking down of complex ions by action of electrolytes arising from the exchange reaction, and sometimes by supersaturation or supercooling of the solution. And another point is that filtration effect, which helps precipitation of components when hydrothermal solution filters through the poorly permeable rocks and mineralize the rocks in front of such barriers. So these are the factors that promote the mineral deposition. The major is temperature changes, pressure changes, the reaction between the country rock and the fluid, change in pH and EH of the medium. These are some of the important factors that control the mineral deposition from hydrothermal fluid in the cavities available in the host rocks. Following are the sequence of mineral formation or paragenesis. It is seen that there is an orderly sequence of mineral formation from hydrothermal solution. That is, first the quartz is found to be deposited, which is followed by iron sulfides, arsenides, sphalerite, energite, chalcopyrite, bornite, galena, gold and silver. This sequential arrangement is called paragenesis. In a normal condition, the hydrothermal fluid gives rise to these type of deposits, so they form the mineral paragenesis from hydrothermal fluid, that develops from hydrothermal fluid. Let us discuss on the classification of the hydrothermal deposits. The hydrothermal deposits are classified on the basis of the temperature formation or on the basis of the mode of formation of the deposit. If you take into account the temperature of formation, the hydrothermal deposits are classified into four types: hydrothermal hypothermal deposit, mesothermal deposit, epithermal deposit and telithermal deposit. And also there is another type of deposit, that is genothermal deposit. So these five types of deposits are made on the basis of temperature of formation of the ore minerals or mineral deposits from hydrothermal fluid. Hypothermal, as the term indicates, hypo means below. So the hydrothermal fluid at a greater depth in a temperature range of 300 to 550 degrees centigrade gives rise to economic mineral deposits such as kolar gold, sulfides of gold that occur in silicates, quartz, garnet, tourmaline, mica, amphiboles and pyroxenes. These are the silicates that form, and sulfides of gold are found to be deposited at this temperature range, and it is generally at a greater depth. That's why the deposit described as hypothermal. In case of mesothermal, the temperature range is around 200 to 300 degrees centigrade, and pressure ranges is about 140 to 400 atmospheres. Depth is around 1.5 to 4 kilometers. So this takes place at an intermediate depth compared to the hypothermal deposits. And similarly, here the sulfides of copper, lead, zinc, gold, silver, they are found to be deposited. In case of epithermal deposit, epi means above, so it takes place near the surface of the earth, or we can say it develops at shallow depth away from the ground surface within a temperature range of about 50 to 200 degrees centigrade. Here the rich fissure filling deposits or the bonanza of gold, silver, copper, mercury, lead, zinc may be found. So these are epithermal mineral deposits which develop at shallow depth just below the ground surface at a temperature range of 50 to 200 degrees centigrade. Besides these three major types, there are telithermal deposit. Here the deposit develops under low temperature pressure conditions, but it takes place far away from the parent igneous body with which its genetic relationship is not well established. the meteoric water may get remotely connected with igneous activity in order to give this type of deposit. So, genetic connection is not there and it takes place at low temperature pressure conditions, and the deposits are described as telethermal deposit such as the sulfides of zinc, lead, copper, iron. These deposits are found by this process. Another method of mineral formation is xenothermal deposit. Here the deposit is formed at high temperature from ore fluids expelled from the huge igneous masses which have intruded into the shallow depths. Thus, it represents high temperature, shallow depth deposit formed by rapid cooling. So, it is a high temperature deposit, but it is found to be expelled from huge magmatic bodies. So, these are the 5 types of hydrothermal deposit on the basis of the temperature changes. And now, let us discuss the type of hydrothermal deposit on the basis of the mode of formation. These are of 2 types. They are cavity filling deposit and metasomatic replacement deposit. These are the 2 types. So, what is cavity filling deposit? That means cavities are there in the country rock, and these cavities are found to be filled up by the mineral fluid or from the hydrothermal fluid. So, the cavities are found to develop in a rock at the time of its formation or later to the time of their formation. Accordingly, they are described as primary or secondary, and these cavities are found to be filled up. So, in order to give rise to this type of deposit, the cavities are essential in the country rock. In natural process, the country rocks present numerous types of openings, cavities, such as in form of fractures, joints, cracks, faults, bedding planes, shear planes, solution cavities, pore spaces, vesicles, lava drain channels, etc. So, these are the different types of cavities that are found to be present on the rock bodies. These cavities are grouped into 2 categories, that is original or primary cavity, which develop in the rock at the time of its formation, such as pore spaces in sediments, crystal lattices, vesicles, bedding planes, etc. But most of the cavities are found to be developed in the rock after their formation. They are said to be induced secondary cavities, which develop in the rock after their formation. They are different types of joints, shear zones, solution caves, collapse breccia, tectonic breccia, cracks resulting from folding, faulting, shearing. So, these are the induced or secondary cavities that are found to be present in the rocks. The deposition of hydrothermal fluid in cavities takes place due to change in temperature, pressure and chemical characters of the mineralizing solution. The characteristic features of cavity filling deposits are crustification, comb structure, box or trusses, massive and cockador. These are some of the features that are there in cavity filling deposits or that are considered to classify the deposit to be a cavity filling deposit. So, what is crustification? What is comb structure? Box? Let us discuss. Let's discuss what is crustification. The minerals which precipitate fast from hydrothermal fluid in the cavities lines the walls of the cavity. Over this lining of the on the wall, the crystals grow inwards into the cavity. Generally, successive layers of different minerals are deposited upon the first one. This process is repeated till the cavities are completely filled up. A filling of this type is called crustification. A crustified vein is said to be symmetrical if the similar mineral crusts are found on both sides of the fissure. Otherwise, it becomes asymmetrical when unlike layers different in number are deposited. So, in case of cavity filling deposit, the first feature is the lining. If this is the cavity, first the minerals are deposited over the walls, that gives rise to the first layer, that is lining. And then over this lining the minerals are deposited. The minerals are found to be deposited in one layer or many layers. The minerals may be of one type or many types. And the cavities may be fully filled up or partially filled up. And when these minerals that grow inwards fill the cavity, it gives rise to a crustified vein. If on both sides the crust produced are of same type and same in number, in that case it is symmetrical crustified vein. Otherwise it becomes asymmetrical. Then what is comb structure? During crustification, the minerals present euhedral structure that project into the center of the cavity. This process of growth of the cavity wall, growth of the minerals from the cavity wall produces up and down pyramidal forms of the crystals that look like the structure of a comb. That is why the arrangement of minerals filling the cavities provide the comb structure. If this is the cavity, first there will be lining, then the minerals will grow like this. It will grow like this. This type of arrangement, here we see this type of arrangement is called as the comb structure, because the pyramidal forms of crystals are found to project inwards into the cavity from the cavity wall. So this structure is comb structure, and when the comb structure completely fills the cavity, it gives rise to crustified vein. But in many cases, the mineralized vein that develops from the hydrothermal solution may not always completely fill the cavity. That means open spaces, gaps may be found within the cavity unfilled by mineral matter. These gap or open spaces that are found in the cavities are called bogs or drusses. If the cavity's filling deposit is made up of one mineral, then it is not called as a crustified vein. So crustification is absent and the deposit is said to be massive. Cavities filled up by one mineral, that gives rise to a structure which is described as massive. In case of cockade ore, that is, the crust is found to surround a brachia, or it is a type of brachia filling. Here it is called as a cockade ore. So this is the general figure of a crustified vein. These cavities are called vogs. This is comb structure. First there is lining, then minerals, different mineral layers have been developed. We have the galena layer, calcite layer, quartz layer. So it is a crustified vein with comb structure. And this type of structure is very common in case of cavity filling deposit. Depending upon the nature of opening, the cavity filling deposit occurs in a variety of shapes and sizes. The common type of cavity filling deposits are fissure veins, shear zone deposits, stockworks, shadow leaves, ladder veins, solution cavity fillings or cave deposits, pore space fillings, vesicular fillings, brachia fillings, pitches and flats. So these are the different types of cavity filling deposits, and they are related to the type of vein that the hydrothermal deposit is associated, and deposition of hydrothermal minerals takes place in those cavities. So let us discuss these different types of fissure veins or the cavity filling deposits. So what is fissure vein? So as the term indicates, it is a fissure. In the fissure, the veins of minerals are deposited. A fissure filled with ore is called a fissure vein. What is fissure? It is a tabular in form and occupies one or more. This fissure vein is tabular in form and it occupies one or more fissures within the host rock. The host rock presents cavities, fissures, long, deep cracks, which are the fissures. The common deposits include metallic sulfides of gold, silver, copper, lead, zinc, and mercury. Most fissure veins are narrow and the length ranges from few hundreds of meters to few kilometers. Within the fissure vein, there occurs unequal concentration of ore minerals. There are places where the concentration of ore is very large. There, the ore is described as the ore shoot. The term bonanza is used to refer the exceptionally high grade ore in the ore shoots. The bonanza is usually small and discontinuous. It results due to localized enrichment of the ore fluid with the metallic components. Example, magnesite in Salal area of Jammu, Kolar gold deposit. So, the fissures, they are found to be filled up by mineral matter, mostly metal deposits. Fissures are found to be very long cracks, and the fissures may be of different types based upon which we have different types of fissure veins. They are simple fissure vein. Here the fissure vein occupies a single fissure whose walls are straight and parallel. Chambered fissure vein. When the fissure presents irregular branching of the brecciated, particularly irregular branching found in brecciated wall, the ore vein deposited in such branching fissures constitute chambered or chambered fissure vein. Sometimes these vein ores enclose pieces of country rock completely. These enclosed pieces of country rock are called as horses. So, chambered. Here it may be pieces of country rock. They are called as horses. This type of deposit, chambered, or it may be dilated or lenticular vein, like lenticles. In schistose rocks, ore deposition may take place along schistosity planes in form of disconnected lenses, pinches and swells. Pinches and swells, like, or it may be sheeted vein, where the veins are parallel, where the veins are closely spaced and parallel. These fractures are filled by mineral matter and it produces sheeted vein. Similarly, where the parallel fissures are cross-cut by diagonal fissures, the mineral matter filling these parallel and cross-cutting fissures constitute composite vein. The width of such veins may range up to several tens of meters. So, based upon shape, size of the fissures veins are described with different terms. It may be composite vein, it may be sheeted vein, it may be dilated or lenticular vein, it may be chambered vein, it may be simple fissure vein. So these are the terms that are used to describe different types of fissure veins. So this is lenticular, this is sheeted, this is chambered. Besides these fissure fillings, there are other types of openings, and the deposits are accordingly described. For example, shear zone deposit. So the shear zones are associated with faulting. So the shear zones present a number of parallel planes of joints or fault planes or shear planes with large surface area through which the ore bearing fluid passes, and it gives rise to mineral deposit under suitable conditions under suitable physico-chemical and environmental conditions. Example, Singphum shear zone giving rise to copper deposit, Singphum copper. Then stockwork. Here the rock body presents a network of cracks interlinked with one another. These cracks get filled up by mineral matter from circulating hydrothermal solution. The veins produced show stratification, comb structure. The spacing between the veins varies from few centimeters to few meters. This type of deposit is called stockwork, and here in order to recover the ore, the whole rock is found to be mined because the cracks are interlinked with one another, and it is very difficult to separate one crack from the other. That's why the whole unit is being mined in order to recover the ore. Example, Kaleen and sphalerite deposit in dolomites of Jawar, Rajasthan, asbestos stockwork in Archean rocks of Barabana area, Singhbhum, Bihar. Then saddle leaf. It results when the alternating competent and incompetent beds are found to be folded with their crests presenting openings, and these crests are found to be filled up by mineral matter from hydrothermal fluid. So the crest regions of the folded beds, they are found to be filled up by mineral matter here. These are called as saddle leaves. Because of tension, cracks develop or open spaces develop along the crest regions, and which are found to be filled up by mineral matter passing through the bedding planes and showing concentration of deposit in the crests. The very shape of the mineral vein is like that of a saddle, and therefore it is called as saddle leaf, such as quartz reefs in Hutti gold field, Wayanad gold deposits of Tamil Nadu. Now let us discuss what is the ladder vein. Vein showing a ladder type of shape. The dikes intruding into the country rocks are discordant bodies that cool and consolidate with the development of transverse fractures to the dike wall. These fractures subsequently get filled up by mineral matter from hydrothermal fluid. The very appearance of the minerals occurring in such dike is more or less resembling to that of the ladders or the rungs of the ladder. That is why this type of deposit is called as ladder vein. Intrusive dikes, they develop transverse cracks, and the ore-bearing fluid passing through these gives rise to economineal deposit here in these cracks. So these cracks, transverse cracks present in the dikes, are filled by mineral matter, and this gives rise to a ladder-like appearance. These deposits, they appear at the rungs of the ladder. That's why it is called as, described as ladder vein deposit. Example, magnesite deposit of Mysore, asbestos deposits in Kadapa district, Pulivendra asbestos, Andhra Pradesh. So these are the ladder veins. Besides these, we have the solution cavity deposits. Limestone countries present joints, cracks and solution cavities. It is due to leaching of calcium carbonate in form of calcium bicarbonate by reaction of percolating groundwater charged with carbon dioxide that takes calcium carbonates into solution in form of calcium bicarbonate. As a result of it, the caves are produced in the limestones, and these caves may be filled up by mineral matter from hydrothermal solution, as is seen in case of barytes of Krol limestones, Sirmur district of Himachal Pradesh. Then let us discuss what is pore space fillings. Pore spaces are there in the sedimentary rocks. Sedimentary grains are sedimentary rocks are made out of sediments, and a number of pore spaces are available between the grains. These pore spaces are found to be filled up by mineralizing fluid passing through these porous rocks. Porous and permeable sedimentary rocks such as sandstones provide channel through their pores for the circulation or passage of hydrothermal fluid and deposition of mineral matter under suitable conditions of lowering of temperature and pressure. Example, disseminated lead and zinc in gritty conglomeratic sand dolomites and quartzites of Jawar, Rajasthan. Then vesicular fillings. The vesicles are found to develop in the volcanic rocks, and the vesicles may be found to be interconnected, and these interconnected channels in the volcanic rocks provide the passage for the hydrothermal fluid, and this hydrothermal fluid under suitable conditions of cooling and reaction gives rise to vesicular veins. For example, copper deposit in Dras volcanics of Kargil area, Jammu and Kashmir. Agate, chalcedony and amethyst deposit in the Deccan troughs of Gujarat and Maharashtra. Because a lot of vesicles are there in the vesicular basalts that form the country rock of the Deccan troughs. So numerous vesicles are there that are seen in the Deccan basalts, and these vesicles are found to be filled up by these minerals: amethyst, chalcedony, agate, feldspars, rock crystals. So these are the vesicular fillings. Brachia fillings. The brachias are the sedimentary rocks that present pore spaces between the angular grains or rock fragments, which provide the site for mineralization. The brachias may be volcanic, may be tectonic, or it may be collapsed brachia. Example, Vajrakarur kimberlite pipes of Andhra Pradesh, providing the diamond deposit, diamond, Singhbhum shear zone, Bihar, showing copper, lead, uranium, apatite as brachia fillings. Then let us discuss what is pitches and flats. These are the ore shoots or the chimneys. Folding in brittle sedimentary rocks causes openings in disconnected manner in series. When these openings are filled up by rich mineral matter, that is ore shoots, they are described as pitches and flats. Pitches are elongated pipe-like ore shoot within a lode or vein that plunges downwards along the vein. The flats are essentially horizontal, gently inclined ore body or ore shoot in a vein. So pitches are dipping, flats are more or less horizontal. The iron ore deposit in Boiladila, Chotnagpur of Bastar district, MP, lead zinc deposit of Baghamari in Banka district of Bihar, place is Katuria. In talc deposit of Kannur, Calicut district, Kerala. So these are some of the cavity filling deposits. cavity filling deposits that are found to develop from hydrothermal fluid, and the types are described with respect to the type of cavities that are found to be filled up by mineral matter. And very important of the cavity filling deposits are the fissure veins. Fissure veins, ladder veins, saddle ribs, stockwork. These are very common cavity filling deposits. Now let us discuss about metasomatic replacement. In case of metasomatic replacement, the deposits formed when hydrothermal solution invading into the country rock through different kinds of openings or pore spaces or fractures react with the minerals of the country rock, and this reaction causes dissolution of the minerals from the country rock, and in its place deposition from the hydrothermal fluid in the place where the removal of mineral takes place through reaction. And the replacement that takes place is here described to be molecule per molecule, so that the internal structure of the country rock is found to be preserved. This is the process. Molecule per molecule replacement takes place and the structure is preserved. So the chemical composition and physical characteristics of the host rocks and the minerals and the composition of and temperature of and pressure of the invading mineralized solution determine the efficiency of this process of mineral formation. Because the country rock must be of suitable composition, and the mineralizing fluid that is passing through these cavities that must contain suitable components so that reaction between the country rock and the invading solution can be possible, and under this condition the deposition can be possible. If the reaction is not possible between the invading solution and the country rock, deposition cannot be possible. So it is related to this type of deposit is related to the chemical reaction that develops between the invading solution and the country rock. Here, how the metasomatic replacement deposits are identified? There is no classification, and there is presence of pseudomorphs of replacing mineral after the replaced ones. As I have already told, the replacement takes place molecule per molecule, and a mineral which is being replaced by the replacing mineral, the replaced mineral takes the shape of the replaced mineral. So here we can say the replaced mineral is the pseudomorph, or it is taking the false shape of the replaced minerals. So pseudomorphs are common. There is no classification in case of replacement type of deposit, and there is extremely irregular outline of the ore body, because replacement will take place through reaction between the country rock and the invading solution. So reaction may go inside or it may exist near the surface. So the outline is found to be irregular, and the presence of remnants of country rock in unsupported condition, that is a common feature. If it is a country rock, the solution passed like this and deposition took place like this, in this manner. So this part of the country rock becomes separated from the original rock body, and it is being found to be enclosed by the ore deposit. So it is found to be unsupported. This country rock is found to be unsupported, and it is found to be supported by the ore materials. So this feature is possible because of the deposit provided by the mineralizing solution. So it gives rise to pseudomorphs, it gives rise to irregular outline, it gives rise to unsupported country rocks. And the preservation of original rock structures such as stratification, bedding, fossils, they are all found to be preserved because the replacement is molecule per molecule. One molecule is replaced by simultaneous with deposition of another molecule from the mineralizing solution. And there occurs doubly terminated crystals of ore transecting rock grains of the enclosing rock. The ores are found to be doubly terminated crystals. They transect, that means they cut across in transverse manner. Transect, cut across the country rock in transverse manner because of its reaction with the country rock. The intersection of diversely oriented host crystals, it develops due to reaction. Reaction will proceed in which direction, that cannot be said. So depend upon the reaction, depend upon the solution, the wall-lock is found to be affected, showing very irregular shape, and accordingly the deposits that develop in the place where the reaction and solution takes place, it becomes irregular. Small wavy veins of irregular width which transect host rocks indicate replacement. So all these are related to reaction between the ore bearing fluid and that of the country rock. So how much charge is the hydrothermal fluid with respect to chemicals present, with respect to its temperature, and what is the composition of the country rock, that can yield to this hydrothermal fluid, so that reaction can take place in proper direction, so that the deposition from mineral fluid can be possible. The process of metasmatic replacement can be summarized as the following. The replacement is a chemical process of simultaneous capillary solution and precipitation. By this process, new minerals are substituted for earlier minerals and rocks. Replacement occurs through the action of hot vapors or hydrothermal solution. The new minerals are carried in solution to the site of replacement, and the replaced ones are brought into the hydrothermal solution. Thus, it is an open circuit and not a closed one. Replacing minerals give rise to deposit, and the replaced minerals are brought to the solution. The replacement takes place molecule per molecule. That means one molecule of country rock is replaced simultaneously with deposition of another molecule from the hydrothermal solution. This process helps to preserve the shape, size, texture, structure of the replaced mineral or rock. Therefore, the pseudomorphs of different minerals after the replaced minerals are found to be presented by these replacement deposits. Almost any rock may be replaced by ore of hydrothermal solution, but the carbonate rocks such as limestones, dolomites are very susceptible to replacement. Closely spaced sheeted fissures and shear zones, because of their large specific surfaces, give rise to large scale replacement deposits. If these fissures are present in limestone countries, that gives rise to good amount of replacement deposits. The replacement takes place in an order. That is, the first formed mineral or minerals are the ferromagnesian minerals. So the replacement takes place in an order. What is that order? The first formed minerals or ferromagnesian minerals are replaced by later ones. So the ferromagnesian minerals are replaced by later ones first. The sequence formed in common primary metallic deposits are pyrite, energite, tetrahedrite, sphalerite, chalcopyrite, bornite, galena and silver. So in this order the minerals are found to be deposited. This is the order. Pyrite followed by energite, then tetrahedrite. In this order, finally by silver. Pyrite and arsenopyrite are the first formed metallic minerals and are replaced by the later formed minerals. In case of rocks, the ferromagnesian minerals are replaced first, followed by feldspars and quartz. So here is the order of replacement. First, the ferromagnesian minerals, it may be biotite, amphibole, pyroxenes. This is the host rock. They are replaced by chlorides and sulfides. This type of alteration is called chloritization because chlorides are developed. These minerals are replaced by chlorides. So it is chloritization. In second phase, the feldspars, orthoclase, plagoclases, they are found to be replaced. First ferromagnesian minerals, then silicates. So they are replaced by sericite, kaolinite. The process is called sericitization, kaolinization. It takes place in the second phase. In the last phase, the silica is found to be replaced by silica and carbonates. The process is called silicification and carbonate replacement. Following are the different types of replacement mineral deposits. They may be massive, they may be replacement load deposits, they may be disseminate deposit. What is massive? Here the deposit that results is found to be very uniform, dense and compact with little or no gangue or no country rock in between. The deposit appears to be very irregular and varied in sizes. It may thicken and thin with wavy outline and ramify irregularly in all directions. The replacing minerals terminate abruptly with the country rock. The host rock is found to be limestone. Example, Khetri copper, lead, zinc deposit of Rajasthan, skarn deposits in the limestone countries, Mississippian Valley lead zinc deposits. Then let us discuss the lode deposit or vein deposit. Here replacement is found to be localized along thin beds or fissures, vein-like. The replacement may start from the fissure with a bold front or some prominent centers followed by replacement at many centers. The outline of the ore body may be wavy, irregular and gradational with the country rock. It may resemble fissure vein, stringers, stockworks in form. However, it is wider than the fissure vein with walls very irregular. The deposit appears vein-like, lenticular or needle-like, irregular body along fissures and bedding planes. Example, limestone dolomites replaced by pyrite. Lead zinc deposits of Jawar replacing the limestones and dolomites. Kolar gold, Hutti gold in Karnataka. This disseminated replacement deposit. Here the ore minerals are found to be scattered, dispersed through the large volume of the host rock instead of forming a concentrated vein or massive pure ore body. It results due to replacement taking place in multiple centers. The grade of ore is found to be very low with texture fine grained and the deposit is very large with respect to tonnage. It requires large scale open cast mining. The host rock is commonly igneous rock. It may be granite, diorite, or it may be sedimentary sandstone shells that give rise to these disseminated deposits. Example, porphyry copper deposit. Host rock is quartz, monzonite, granodiorite country rock. Example, Bingham Canyons of USA. Near Salt Lake City of Utah. Singhbhum Copper Belt, Jharkhand. Tungsten deposit of Degana, Rajasthan. Uranium in Tumelapalli of Andhra Pradesh. So these are the stockworks, saddle leaves, ladder veins, limestone caves, cave deposits, replacement ore, unsupported rock, replacement deposits, replacement around fractures, forms a massive ore. So these are some of the figures that show the cavity filling and replacement type of deposits. These are mostly replacement type of deposits. So replacement types are disseminated type, lode type and massive type. Its replacement takes place in a order. Ferromagnesium minerals are replaced first, followed by feldspars or silicates, finally by quartz. Through processes like chloritization, sericitization, kaolinization, silicification, and this replacement is controlled by the chemistry of the wall rock and the chemistry of the embedding solution, temperature and pressure condition of the embedding solution, and the cavity filling types are based upon the type of cavity which are found to be filled up by mineral matter from the hydrothermal fluid. Depend on the shape, size of the cavities, the different types of cavity filling deposits are described. So, this is all about the hydrothermal mineral deposits which give rise to the epigenetic mineral deposits from the hydrothermal fluid. So, this is all about the hydrothermal deposit that I wanted to discuss. I thank you all for